they're still pulling the other one in here. And then you see this is this acoustic release that sits at the bottom and it holds on until we ask it to let go. We had John Myers from the news trip out with us today. Just curious to know what we were doing. These are the thermistors. This is what you're holding right now. You can see they're in these white brackets, and we clamp them onto the cable with these clamps. And somewhere here they're going to start. Yeah, there was already fishing nets out. I'm not sure exactly what season it is right now, but up near McQuaid there was a fishing net out. Some bunks. So here's a pair of these releases that we're going to put under this buoy. This is a PAR sensor that we put underwater. It measures photosynthetically active radiation, and that's about 3 meters depth. So we have radiation measured at the surface, but also at 3 meters depth, to see basically how turbid that upper layer of water is. First shots. And then just, there are so many things that can go wrong. We spend an enormous amount of time just looking at every little thing. It's a little bit, so here now they're lifting the buoy. It's almost like a movie or some pictures. And they're lifting it over the side. And you see here there's this cable that's yellow and black. The yellow is the actual strength member that actually takes the tension of the buoy. And then we've attached a cable that has temperature sensors on it so that we get that temperature from as deep as 40 meters, about 130, 140 feet down. We get those temperatures in real time in our lab. And so here it is going to the side, in the water, into the tag lines. And then it floats free, and we flake everything else out over the side. This looks like it got banged or something like that. And I don't know if I had the chance to write all of these images. These here are floats. There are big glass balls inside each one of these. They provide flotation on the mooring line. You can see we're going to put more of these autonomous thermistors in as well. And kicking more floats over the side. And then here, what do you think these are right here? This is what we use for the anchor. Can anyone tell what that is? The railroad wheels. We buy scrapped railroad wheels, and it takes 6 of them to hold this thing in place. This is actually one of the larger expenses because we don't get those back. We kick them in, and then at the end of the season, when we recover it, we don't get the wheels back. But we kick them over to the side. We have a crane that lifts up this platform here. And they slide in the water and make a big splash. Oops, and then I think that's about it. So at that stage, the buoy is in, and we head home. So anyway, I pulled out those thermistors I mentioned. Do I still can chat for a little bit?
Yep.
Okay. I'm gonna click to yet another thing, and so I've not had a chance to look at any of this data yet, but I did get it to a point where I can just about play with it, and I just wanted to show you what a little bit of this looks like, and we'll see if we can put a date axis on this too. So we have some dates. And so this is the raw data out of 3 of these loggers. I didn't have a chance to get all of them working yet, or all the data out of all of them yet. And this is utterly as raw as the data can be. And I just want to give you a sense that none of this is perfect. Okay, this is science is messy, but far messier than a textbook makes it look. Although you're all teachers, so you will presumably understand this. These high temperatures here. This is what the loggers were telling us when they were sitting on the deck of the boat before we put them in the water. Likewise, this is the temperature outside when we took them out. So we're really not interested in that. Here, what we're seeing is the water warming below 4 degrees Celsius, and then really being, because this is a relatively shallow, it's in about 50 meters of water, we don't see a huge amount of stratification form. Most of the mixing at the surface is able to mix the entire water column from the surface all the way to the bottom. Although you see in this season here, this is a season where ice is starting to form, and we can zoom in on that a little bit. Again, I haven't looked at this, so I have no idea exactly. Not that I expect we're going to find anything really dramatic, but I haven't had a chance really to look at this carefully. These thermistors are accurate to about 2/1000ths of a degree. We calibrate them in-house. And you see that this scale is not very large. Here's 0 degrees, here's 1 degree. These periods here, where it gets very, very close to 0, are probably periods where there's ice at the surface. You can see that some stratification is forming in this period when there's a fair amount of ice. And I think you can start to see, let's zoom back out, you can start to see the warming of the water column right here. This is clearly bad data. Something happened here that caused the temperature to jump up and then jump right back down, so we ignore that. And you can see right here, the sort of stair-step form you see here is the daily warming cycle, where it warms up when the sun is out during the day and then sort of cools off a little bit at night. So you see it sort of wiggling here, and it's warmed up from really very close to 0 through the entire water column up to about 1.4 degrees as of today. So that's what this data, in its very rawest form, looks like. Okay, and again, I haven't had a chance to really spend time make sure that it's of high quality or anything like that, but that's where we start. I'd mention just 2 other quick projects that are really sort of fun. This is part of a different project, although we're on the same boat, obviously, as again the Blue Heron. This is an autonomous underwater vehicle or underwater glider, AUG as they're called in the biz. And it doesn't have any propellers or anything like that on it. It propels itself by changing its density. So it has under its nose cone, it has a little bellows, and it can pull that in or push it out and change its effective displacement volume, and thereby change whether it floats or sinks. When it sinks, when it makes itself more dense, it has a set of batteries in this forward hull section that it pushes forward, so the whole thing tilts down like this, and then when it sinks forward. And then when it decides that it's deep enough, it pushes that bellows out under the nose cone again, pulls those batteries back, and it swims up. So it swims in this zigzag pattern. And the nice thing about using this as a method for propulsion is that it's remarkably power efficient. On a single set of batteries that this thing has in it, this thing could theoretically swim from here to Sault Ste. Marie and back. So it would do it very slowly. It would take about a month to do that. But the point is that you can have these things out autonomously for a very, very long time. This is a picture, this is sort of the scariest moment of all, when you sort of push this thing away from the boat. Because when we do this, we'll send it out for 2 weeks at a time. And you go out there on the boat and you put it in the water and then you go home. And you can talk to it. It comes to the surface every now and then and sticks its tail feathers out of the, you can see this tail here. It sticks that tail out of the water and then it can communicate through a set of satellites with us. And so we can give it new commands and it can send us data and all these programs. And it navigates by, it has a GPS in here. So when it comes to the surface, it knows where it is using that GPS. And we give it waypoints, we give it locations, go to A, then to B, then to C. And it just follows that, and goes in a pattern. This is a section we did from 2 harbors on this side to Port Wing over here. The colors here are temperature, with red being warm temperatures and blue being cold temperatures. This is the distance across the lake in meters, unfortunately, so it's 10 kilometers, 20 kilometers, 30 kilometers. And this is the depth on this axis. So you see this warm layer of water at the surface, and this very interesting bulge here as well. And one last thing that I want to talk about, unfortunately I could not find my pictures from this. In January I was in Malawi, which is right here, and Malawi is home to Lake Malawi, or Lake Nyasa, depending on who you ask, which is one of the great lakes of the world. It's up to 700 meters deep. I think it's the 6th largest lake in the world by volume. It has a phenomenal, I think the largest number of indigenous species of any lake in the world, mostly cichlids. I think there's a picture here, just an astounding variety of fish. And then Lake Tanganyika and Victoria to the north of that. But we're over there doing a project doing sort of ecosystem characterization. I'm sort of the physics guy going in there and doing the same sorts of things, putting temperature loggers in and trying to understand how the temperature structure of a lake like this responds to climate change. The interesting thing about this is that these lakes, because they're tropical, don't have these strong seasonal effects effects like we do up here in mid-latitudes. So this lake is permanently warm at the surface and very slightly cooler below. And what we're very interested in is how we can, how those lakes are going to respond differently or the same. What is similar and what's different about these sorts of lakes when it comes to not just their physics, but the ecosystem as a whole. This is a very important lake because a vast majority of the protein for the nation of Malawi, which sits over here on the western side of the lake, a vast percentage of the protein they eat comes from the lake. Fish is a staple of their diet. You can see here these dugout canoes. And I always thought that this was all sort of, stereotyping. I don't know how to put this, but I went over there and they all do indeed go out in dugout canoes and catch fish, with little nets they drop over the side and stuff like that. So this is a very typical scene along the coast there. So it's important for understanding, what we're trying to do is understand how changes in the water regime in that part of Africa could affect not just sort of the basic ecosystem of the lake, but how people perceive the lake and how people interact with the lake. It's going to have a huge impact on fisheries, huge impact on water levels. There are huge numbers of things that make understanding these sorts of systems very, very important as well. So that's what I have for now. Mildly disorganized, but hopefully there's some questions and we can fill in some of those holes there. So that's what I got. So thank you very much. So my favorite parts of these things are people